Hey y'all, so the purpose of this video is to try to look at a couple more complicated situations, right? Not necessarily more complicated circuits, but just where we're starting to evolve a little bit more, trying to look at some, let me show you. For example, this, in our notes packet, this is example number 15, all right? Now, you'll notice that this looks very similar to one of the circuits that we did earlier. We're just combining it then with a full circuit, with a power source, where it's starting to ask us about current. So it's not just about the resistance. But what we learned in that previous video about resistance and putting resistors together to get a total effective resistance, we're going to be using that here. All right? So in this question, we have a 3-volt EMF, power provided, potential difference, right? The current is going to flow out of there. Okay, it has labeled this as current 1. So the current goes through here. All of that current is going to go through the 3 ohm resistor here. Then it's going to get to this point. It's going to split and go through the 9 and the 6. Right? Now the reason why it's now labeled these as separate is because remember right here, this is all current 1. That's all the same current. The current going through here is the same as the current there, same as the current there. All of that, as long as it's just this single wire all the way around, that's the same current. However, as soon as we split it, we now have the current splitting to go through those different sides. So one current's going this way, one current's going that way. All right? And so therefore we have a different amount of current. Now we do know that because it's a parallel circuit that when they come back together, it will again equal I1. So I2 plus I3 equals I1. And you know what the heck? I'm just going to write that down just in case. Right? That, by the way, is one of Kirchhoff's laws. We're not going to go into Kirchhoff's laws this year, but you may see that in the future if you go forward with physics and circuits and things like that. But yes, so we know that just conceptually understanding the idea of current and things like that, charge. All right. So now what we want to do is we want to be able to find the current in each of these. Okay. Now if I have this potential right here, 3 volts for the whole circuit, right? But I don't have a resistance for the whole circuit, right? I don't have a resistance for a single piece. I do have the resistance here, but I don't know the current going into it, and I don't know the potential difference across it, right? Because there's going to be some potential lost here, and then some potential lost over here, right? And so I'm kind of at this point where I can't work with these individual pieces. However, this is where that idea of putting things together and getting a total effective resistance comes into play. Because what we're going to do is we're going to put all of our resistors together and say, what would the total resistance be? If I can figure out what the total resistance would be, then I can use the total EMF to get the total current. All right? So the first thing I'm going to do is I'm going to put these two together, right? Now those two are in parallel. And so I'm going to go 1 over 9 plus 1 over 6 equals 1 over the resistance. I'm going to label that resistance parallel, the parallel piece of the circuit. So we're going to go 1 over 6 plus 1 over 9, and then that will be equal to 1 over our piece, so I need to do 1 over that. Okay, so then I'll just 1 over that, which will give me 3.6. Okay, remember that when you add these together, that's still just this. You still need to flip it. You need to do 1 over that or do the math to solve for it. So this is 3.6. So essentially what I have now is I have a 3 ohm resistor followed by a 3.6 ohm resistor. Now, of course, I can put those two together because that's now a series circuit. So I can add those together, and when I put series together, then I just add them. And so I go 3 plus 3.6. So the total resistance here is going to be 6.6 ohms. All right? So that is, if I put all of these together, I end up with 6.6 ohms. All right? So with that, I can now look at the whole circuit. So I'm looking at the circuit as an entirety, so I'm going to use the same blue that I used here, and I'm going to go V equals IR for the whole circuit. Okay, so the potential going through the whole circuit is 3 volts. the current going through the circuit is going to be that I1. And then the resistance of the whole circuit is this 6.6. And so now I can solve for I1 just by going 3 divided by 6.6. And I get 0.454545. So I'm going to go I1 equals 0.45. And then 4545. I'm just going to stick to the two significant figures. Everything's in SI units, so that will be amperes. So I got I1. I know I1 is 0.45 amperes. Now I need to find the other ones. Okay? Now the other ones is going to be a little bit more challenging, but we can do this with what we know about individual resistors, individual components, right? We know, for example, that if this current of 0.45 goes through this resistor, I can do V equals IR for that resistor. So the potential across that resistor is going to equal the current, which is 0.45, times the resistance, which is 3. And so I'm going to take that, I'm going to do the 0.45454545. I'm going to multiply that by 3. And I'm going to get a potential difference of 1.36. So therefore, the potential difference across here is 1.36. Now, here's the cool thing, right? Is that this is in series with that, right? So if I had 3 volts to start with, I have to go down 1.36 volts here, then whatever's left is going to be the potential difference of this piece right here. So I'm going to go 3 minus that 1.363636, and I get 1.6363633. And so therefore, the potential difference across here needs to be 1.64. Okay? Now, you may be asking yourself, but meter power, that's 1.64 for both of those, so which one, how much gets out, each one gets what? Well, remember, when they're in parallel, they have the same potential difference, right? That was one of the things we learned in our last video. If I put a 0 here and a 3 here, this wire is 3 volts all the way down. Even when I go through that resistor, that 3 is going to subtract the 1.36, which is going to give me 1.64 right here. This is 1.64, and that is 1.64. The potential only changes when you lose it, when you go through a resistor or a load. If you don't go through anything, then the current just flows and the potential doesn't change at all, right? On this side, it's 0 here, so it's 0 all the way around, which means it's 0 here and 0 here. And you'll notice that this one goes from 1.64 to 0, and this one goes from 1.64 to 0. So they both have a potential difference of 1.64 volts. That's how it works when they're in parallel, okay? So with that then, I can now find the current going through each of those components, all right? I'm going to do the second one right here. This is I2. So I'm going to do V equals IR for the second one, okay? So this is for the 9 ohm resistor, okay? So the potential difference is 1.64. That would be current 2, which is what I'm looking for, and the resistance is 9. And so I can go 1.636363, divide it by 9, and I get that the current 2 is 0.181818 amps. All right? No problem. No problem. We're learning how to use these things both with the whole circuit, but also with individual components, right? So let's look then at I3. So if I do I3, that is the 6 ohm resistor. Okay, so V equals IR. So V, again, is 1.64, equals the current times the resistance, which for that one is 6. And so I'll do that 1.64 divided by 6, and I get this is I3 by the way, is 0.27 amperes. All right, now you may have recognized something early on, but I didn't do it on purpose because I want to show you that, remember we said earlier that I2 plus I3 equals I1? Well, if I take 0.18 and I add 0.27, I get 0.45. Look at that, they add together and it all works. Isn't that great? That's circuits, right? These things have to be true. Okay, it's okay if we have an extra piece of information because that one has to be true as well. So I technically didn't have to do this. I could have just said, well, I1 minus I2 will give me I3, and I could have figured it out that way. I like to do it this way because then at the end I can add them together and make sure that that thing that I knew was true will actually be true. If not, I made a mistake somewhere, right? But if so, at least I've shown that what I have there makes sense given the context of the situation. All right? So there you go. That's that example question. I'm going to go ahead and erase this, and we're going to go on and look at example number 16 in your note packet. All right? So here we go. All right, some great stuff going on in this question now. All right? Now, one of the things that we're going to look at that we haven't really done yet is a switch, right? And IB, AP, all of these, IGCSEs, they love using switches because a switch will change the circuit. And so it's a very easy way for them to use the same problem and say, well, what if, right? What ifs are great. In science in general, that's what science is about. Well, what if we change this? What if we skip this? What if this breaks? What if this damages? What if we switch this, right? So a switch is a great way to do that very quickly and easily, all right? So the first thing we're going to do is we're going to find the current in the 2 ohm resistor when the switch is open. So the open means just like this, that the switch is opened up, which means that no current can flow there. Now hopefully what you're seeing then is that the current will leave the battery from the positive side. It will go through the 2 ohm resistor. It gets to this point right here. It doesn't go there, right? It doesn't go there at all because it can't flow that direction. It can't complete a circuit. So it doesn't even go there at all. It just skips over that, pretends like it's not there. It gets here, it splits, it goes through those two, and then it comes back together, and then it goes back to our cell. Now, what was that? That was a parallel circuit, right? This piece right here was parallel. I could have drawn it differently, right? Where it came here and then it split and it went through the 2 4s and came back together. But it's been drawn slightly differently. And sometimes we do have to look at the situation and say, could I draw this a little bit differently? The understanding is, does the current have to go through both of them? Or does it split, choose, and then come back together? All right? So here, splits, chooses, goes through, comes back together. That's parallel. So when I'm trying to find the current in the 2 ohm resistor, it should be pretty evident that I'm going to need to know how much current is going through that resistor. Now the current going through that resistor is the same as the total current in our circuit. And so for us to be able to do that, we are going to need to do that whole resistance thing with putting all our resistances together. So I'm going to look at the parallel piece here. So that's going to be 1 over 4 plus 1 over 4 equals 1 over the resistance of the parallel piece right here, putting those two together, right? Now, I can actually do this basically in my head, right? 1/4 plus 1/4 is 2/4, which is a half. So 1/2 equals 1 over RP. Do not forget that that's one. I know I say this every single time. It's because one of you is going to forget it anyway. But I'm trying to avoid that. Remember that this is 1 over RP, and so we're going to flip it. And so we end up getting that RP equals 2. All right? So therefore, these are the same as if there was a 2 ohm resistor. And so the current would go through this 2 ohm resistor, it would go through that 2 ohm resistor, and then it would come back to the battery. So we put those 2 ohm resistors together. 2 plus 2 equals 4. Now, if it's helpful for you, redraw the circuit. Instead of having all this, go through a second 2 ohm resistor. I think most of you are okay now saying, okay, so it's just going to go from here through that, that's 2 ohms. 2 plus 2 equals 4. So the total resistance of my circuit equals 4 ohms. Right? That is the total resistance of my circuit. Now, I know the total EMF, or the total potential that's being provided in the circuit. And so therefore I can go V equals IR. So I'm doing this for the whole circuit. The whole circuit is providing 12 volts of potential. I'm going to solve for the current, and the resistance of the whole circuit is 4 ohms. So I divide and I get I equals 3 amperes. So that is the I of the whole circuit, right? So I'm going to label that on here, whole circuit. All right? So that would be this. So that means I have 3 amps going through here, 3 amps going through there, 3 amps going through my 2 ohm resistor. So now the question was, find the current in the 2 ohm resistor. Guess what? We're done. We just did it. We found out that there are 3 amps going through the circuit as a whole, which means there are 3 amps going through the 2 ohm resistor. So there we go. Now it would be different for the current going through these, right? The current is going to split. Now because they're the same resistance, the current will split evenly, and so you'll get 1.5 amperes through here, 1.5 amperes through there. Half the current will go one way, half will go the other way. If they are different resistances, more current will always go to the lower resistance, which makes sense. Take the path of least resistance. Okay, so the current will go in the direction for the least resistance. Okay, now we've already answered question A. Question B changes it. It says, okay, well, what if now we change the circuit? What if we take it and we close the circuit? Okay? Now, what you need to recognize is that this and the 2 ohm resistor are now in parallel, right? The current's going to come here, and then it can choose whether to go this way with no resistance, or it can go up through the 2 ohm resistor. Now, the reality is, if there is no resistance here, all the current's going to go that way, right? If it's low resistance, then most of it will go here and some will go there. But if there is 0 resistance here, which our wires are always 0 resistance, then as the current gets here, as those electrons get here, it's going to say, I ain't taking the path of resistance. I'm going to go the path of 0 resistance. So it's all going to go here, and then it will split. There's our parallel circuit, and then it will come back. And so the answer to how much current is going through the 2 ohm resistor when we close the circuit, well, my dear friends, 0. No current will go through the 2 ohm resistor. And that's because the current will naturally go the direction of 0 resistance. That's it. If there's 0 resistance, the current's all going that way. Okay? Awesome. Next, find the delta V from A to B. I actually forgot to put the A and the B on here. This was A right here. And this was B. So we're going back again to when the switch is open. So the question is, what's the potential difference between this point and that point? Okay? Well, if we think about the model that I described in class, right? This would be 12. That would be 0. So this is 12. This is 12. That's 12. That's 12. This is 12. Now, when I get to the resistor, I'm going to lose some potential there. How much? Well, V equals IR. Now, in this situation, the current we already know is 3 amperes, right? 3, sorry, I don't need the A, that is SI. So 3 is the current because the switch is open. That was the conditions for letter A. So 3 times the resistance, which is 2, and I get 6 volts. Now what that means is that in that resistor, there is a difference of 6 volts. We're going to lose 6 volts of potential as we go through that resistor. So I'm going to go from 12 minus 6 down to 6. Now that means everything in this wire is 6, 6, 6. What that means is that A is at 12 and B is at 6. So what's the difference between A and B? Well, 12 minus 6 is 6 volts. Now, hopefully, that doesn't come as a surprise, right? That should not be a surprise because look, this and this are in parallel, right? The current comes here, those are in parallel, and then it comes back together. So the two things in parallel must have the same potential difference. That's what we learned in the previous video, right? In parallel, that both legs have to have the same potential difference. So therefore, it makes sense that it be 6 volts, all right? Now, the last question is, what would it be when the switch is closed? All right, so we close the circuit. I'm going to have to erase what I got here because none of that's going to, I guess the 12s will still make sense. Okay, there we go. We're going to close that circuit. You get rid of all these here. Sorry, y'all. There we go. All right. Now, this isn't valid anymore because that was only valid when I had 6 amps of current going through there. Okay? But now what you'll notice, I hope, is that this is all the same wire, which means this is 12, that's 12, that's 12. It's all 12, yo! That should make sense because for this resistor, V equals IR. And if the current is 0, so V equals 0 times 2, well, my friends, that is 0. Therefore, the potential difference there should be 0. If there's no current going through the resistor, then it shouldn't cause any potential to be lost. It's just sitting there. It's doing nothing, right? That's what happens when you connect a wire, when you short circuit it so that the current just goes straight through. None of it goes up there. You don't lose any potential there. Of course, whatever that is doesn't work either. If it's a light bulb or a computer or whatever else is up there, it ain't going to work because no current is going there, right? However, we do then know, because this is all the same potential, that the potential from A to B is now, the potential difference is 0 volts. That connects everything that we've said, everything that we've talked about. It all connects, it all makes sense, it all has reason with everything else. Okay, you can't have everything make sense except for one piece. With circuits, every single piece is connected. All right? Okay, hopefully that was helpful with that one. We're going to switch. I'm going to erase this. We're going to do one more question. This is a great question. Very often this question is asked conceptually, but I'm going to go ahead and work through the mathematics of it so that we can actually see. I'm going to connect it to power. Remember, I threw in power there at the end, so we're going to look at some power, but we're also going to look at what happens when such and such happens. All right, so here we go. All right, this is a great question. All right, it's going to combine a lot of the ideas we've been using. It's going to add in power, and it's going to get us really thinking about what happens if. All right, so what we have here is 4 identical light bulbs. Each one is 60 ohms, has a resistance of 60 ohms. We have a 30 volt power source, okay? And the current, as you can see, the current's gonna flow this way. It's gonna split and go through A and B or through C. Then it's gonna come back together and it's gonna go through D. Now, and then it's gonna go back to the battery. Now, I am saying that it starts here and ends there, but we remember, we know that it's all going at the same time, right? And so it's not that these will turn on first and then that will turn on. That's not how it works. They all turn on simultaneously because all of the electrons start moving at the same time. Of course, the electrons are going the other way, but you know, that's another story. We remember that. All right, so here we go. We want to find the power in each light bulb. So to find the power in each light bulb, we know that power equals IV, which I can also connect to the current and the resistance or the potential difference in the resistance if I so desire. Okay, however, I'm going to need 2 pieces of information. Right now I only have the ohms. I don't have anything else. And so what I'm actually going to do now is I'm going to go through, we're going to do the whole resistance thing, because if I know the resistance of all of these combined with the potential, I know the current going through the entire circuit. All right, so the first thing I'm going to do is I'm going to add these 2 together. So when I add those together, those two are in series with each other. Yes, they're in parallel with this one, but I'm going to add those two together because they're in series first. So A plus B, that would be 60 plus 60. That's going to give me 120. So I'm going to redraw it here. Okay, so this is going to go, so I have 120 up here. I have a 60 down there, and then it comes down together, and then I have a 60 right there before it goes back to the battery, right? Now, these two, the 120 and the 60, are in parallel, and so I need to add those together. I can't add these together yet because 120 and 60 are not in series. They're only in series if all the current going through one has to go through the next one. So the current going through 120, that will go through 60, but not everything from 60 is coming from there. Some of it's coming from here. So 120 and 60 are not technically in series. And so we need to combine the 120 and the 60 first so that we can then combine that with the 60. So to do that, of course, I'm going to do the 1 over 120 plus the 1 over 60, and that will give me the 1 over resistance parallel. Okay, so I'm going to go 1 over 120 plus 1 over 60, and then I'm going to do 1 over that because I do need to reciprocate it, and I get 40. Okay, so RP is equal to 40. All right, now if I were to redraw that, it would now look like this. These two have been combined to give me 40, which, yes, by the way, is less than either of those. Remember, that's what we talked about before. And then it will go through the 60. Now that they are completely in series, I can add them together, and I will get 40 plus 60 equals 100. So I now know that the total resistance equals 100 ohms. All right? Now, that is the total resistance of the circuit. Knowing the total potential of the circuit, I can now do whole circuit given that I have a whole circuit now, then the whole circuit is going to be V equals IR, the potential being 30 volts, the current, that's I guess what I'm looking for, and the resistance is 100. I divide and I get the current, the total current, this is the whole circuit, is equal to 0.30 amperes. All right, so we're good. We got the total current of the circuit, but we're looking for the power in each light bulb. Now, right now, I can right away go ahead and look at D, right? Because the current does split here, but it comes back together. So the current going through my cell here must be the same as the current going through the D. That's all one single strand. That's series, which means the current has to be the same through all of that wire. So therefore, I can go V equals IR for the D. The V, I'm going to find out what that is. This is 0.3 for the current times the resistance, which is 60. So 60 times 0.3, and I get 18. So the V here is 18 volts. Now that will come in handy shortly, okay? But remember, if this is 18 and this is 30, okay? If I look at this, right, I've got 30 here, I've got 0 there. So 30 all the way around, this is 30, this is 30, so this has to be 30, that has to be 30, right? It doesn't go through anything there, so that's all 30. On this side, it's 0, 0, 0, 0, but this has to be 18. So if this is 0, this side must be 18, right? Which means this is 18, and this is 18, and that is 18, which means I now know how much potential difference is across C. I also know the total potential difference across A and B. So I know that C goes from 30 to 18, so that is 12 volts. Now, do you have to write these numbers? No, you don't. You can recognize that the whole thing is 30, that's 18, so what's left? 12. You have to have 12 here, you have to have 12 there, because remember, the potential difference doesn't split. It's got to be the same on the top and bottom. okay, when you're going through a parallel circuit. So this is 12 volts. So now I can go V equals IR. The V across C is 12 volts. The current, I can find that now because the R is 60. So I can go 12. Actually, I don't even need that, do I? The current there is 0.20 amps. But the reality is I don't even need it. I actually have everything that I need now in order to be able to answer the question, which is the power in each light bulb. Okay, so I'm going to do light bulb D. So power of D. Now remember, I have a variety, I have several different equations that I can do for power. I have power equals IV. I took the V equals IR, which I put in here, and so then I also have P equals I squared R. And then I also have P equals V squared over R. If I put the V equals IR in for the I, then I have that. And so I actually have 3 different ways that I can get power. So I'm going to use the one that fits for each of these light bulbs. So for D, I have the potential difference, and I have the current, and I have the resistance. Now I needed to get this so that I would know the potential difference here, right? So I had to do that, but I can actually use any of those equations to solve for the power in D. Now I'm going to use the easiest one, which is P equals IV. So I'm going to take the current through there, which is 0.3, times the voltage, which is 18. So 0.3 times 18, and I get 5.4 watts. So that's the power in D. Okay? Now I'm going to move over to C. So now let's do the power in bulb C. So the power in bulb C, I already know the potential difference is 12, and I know the resistance is 60. So if I got V and R, I can use this one. Power equals V squared over R. So I'm going to use that one. So the potential difference was, we said 12. The resistance is 60. So that's 144 over 60. And I get 2.4. Now, you may say, yeah, you can. You can. We knew that the current going through there was 0.2. So you could have used the P equals IV, right? The current being 0.2, the V being 12. If you do 0.2 by 12 times 12, you know what you get? You get 2.4, baby. Yeah, it works. It works. It better work. We proved it all mathematically. It better work. All right. Let's move on. Let's move on to, I guess we're doing DC. We can do B next. All right. Now, we are going to have to do one of two things. Okay. You can either figure out what the current is up there, because right now we have the resistance. We know the resistance is 60 in each bulb, but we don't know the current up there. Now, it's pretty easy to find. You can either solve it. You can, we know that the current here is 0.2 and the current there is 0.3, which means the current up here has to be 0.1, right? Because these two have to add together to give us that one. So you could find the current if you wanted. You can also reason through the potential difference. Because these are identical and they will have the same current, then they should end up having the same potential difference. So if I go from 30 to 18, that's 12. Then that means I must lose 6 here and I must lose 6 there. So it'll go from 30 down to 24, down to 18. Now, putting those numbers there again, you may get to university and your university professor may be like, what's it doing? Huh? Why don't you these numbers? Okay, so the numbers are not correct. It's a model, right? It's just trying to help us visualize and represent the potential through the wire. A better way to go about it is say, well, I've got 12 here it has to be split between those two, therefore it has to be 6. The important thing is not the numbers. The important thing is that the potential difference is 6. The potential difference is 6. But of course, we got the current there too. So it's totally up to you how you're going to solve for PB and PA. I'm going to go ahead and do this. So I'm going to have V squared over R. The V is 6. So 6 squared over R, which is 60. So I'm going to go 6 squared, which is 36. And then divide by 60, so I get 0.6. And then, of course, A has the same potential difference, the same resistance, so that will also be 0.6 watts. All right? And so we've gone through, we did our resistance, we added them together, we put everything together, we worked with the circuit as a whole, we worked with individual components. We've done all of these things in this circuit that have helped us then to put it together to get the power in each light bulb. Now, power is significant because the power in the light bulb is going to show you which one's the brightest. So we know right now which ones are the brightest. We know that D is going to be the brightest. That should make sense because all the current's going through that one. Then the current's going to split, but more current is going to go this way because there's less resistance to go through one bulb than there is to go through two. So more current's going to go this way, so C will be the next brightest. It's the next highest power. These two will both have the same brightness because you're going to have the same potential across each of those. All right? So therefore, brightest, next, dimmest. Now, the next question is, what if A burns out? Okay, well, if A burns out, that's the same thing as opening the circuit. When you burn out a light bulb, what you're doing is something is happening to that light bulb so that it doesn't work anymore. Therefore, the current isn't going to flow. In a normal wire incandescent light bulb, the wire usually gets burnt so that it breaks, it falls apart, so current will not flow. You don't have a complete circuit anymore. So essentially what that means is that this whole circuit here, this piece isn't going to happen anymore. Okay, so there is zero current going through that wire. So what does that mean? Well, that means that my current is going to go from here. It will all go through C. It will all go through D. And then it will come back. So that means I'm going to have to change my work here. All right? So it's not as bad this time. Because this time, all we have is 60 and 60. Those two are in series because all the current has to go through those two. So 60 plus 60 equals 120. So interestingly enough, the total resistance of the circuit went up. Before it was 100 because it was able to split and it was easier for it to flow. But now all the current's being packed through those two, and so my total resistance is bigger than it used to be. Now, why is that important? Well, we are trying to find out how much power is in each of those bulbs, right? So if there's 120 ohms total with 30 volts of potential, then there's two ways to do this. You can either recognize that those are the same, so I'm going to have 15 volts here and 15 volts there, or we can go V equals IR for the whole circuit, which is 30 equals I times 120. I do 30 divided by 120, and I get that the current equals 0.25 amps. Now, that should, in a way, make sense. We have less current than before. Before we had 0.30 amps. Now we only have 0.25. That's because there's more resistance. If there's more resistance, there will be less current, right? V equals IR. Resistance goes up, current must go down, right? So therefore, we have the current, which is 0.25 amps. Now we can see for each individual resistor. And so I'm going to do the power in resistor C. So the power through C, I'm just going to do, I guess I don't know the voltage, I know the current, and I know the resistance. So I'm going to do I squared R. And so that's going to be the current we just said was 0.25 squared times the resistance, which is 60. So 0.25 squared times 60 equals 3.75 watts. What you'll notice is that the power in C has increased. That one's going to get brighter. Why? Because the current doesn't have to split anymore. The current is now all going to go through there. Now, these two were in series, so the current, the resistance, the potential difference there is going to be the same. So that power is also going to be, so power in D is also 3.75. Now you'll notice that that one went down. Well, again, that makes sense. Remember, all the current was going through there. But there's less current than there was before, so if there's less current, the light bulb will be less bright. And so therefore, we can do the mathematics, but we knew that, we could conceptualize that already. You don't have to do the math. You can just think about, well, where is the current going? If the current splits up, I got less current. If the current doesn't have to split up anymore, I got more resistance, right? All those ideas, they come together in these ideas, in these fairly simple circuits, but the math can get fairly complicated just because there are so many things going on, so many things that can be true all at once. Okay? Now, the last question is, what is the potential difference across A? Okay? Well, the potential difference across A is from here to here. Well, here's the thing. If we think about the numbers, this is 30. What happens here? Well, we know there's 30 volts total, which means half of it is lost here, half of it's lost there. So this is going to go from 30 to 15, right? This is going to be 15, 15. No current is flowing through this. However, there is a complete circuit there. So no current, no potential difference is going to be there. So this is still going to be 15. So therefore, this goes from 30 to 15. The potential difference across A is going to be 15 volts. Now, if you didn't understand how I got 15 here, you can always take, we have the current, which is 0.25, the resistance, which is 60. You multiply those together, you get the potential difference across this component right here, which would be 15 volts. All right? Because there's no current here, that's the important thing. Recognize there's no current here, so there won't be any potential difference across this one. That will act just like a normal wire where nothing's happening. And so therefore, the potential difference will be fully across A, because that's where the break is. You'll have this much potential on that side and that much on the other side. Okay? There we go. We finished that question. That's a long one, but there's a lot of great stuff in there. I hope that this has been helpful. I made it as a video so that you can go back, you can watch it, you can double check certain things. If you got frustrated with a certain part, go just rewind it, watch it again, see if you can figure it out. If you can't, send me a message, come visit me, I'll help you through it, and we'll get through these problems, all right? We'll see you next time.